Let x and y be independent random variables, each uniformly distributed on the interval 0 to 1. The transformation z equals the square root of minus 2 log x times cosine of 2 pi y is given. Find the probability density function of z. We use the auxiliary variable method with a Jacobian change of variables. Introduce a second variable w. Form a two-dimensional transformation from x, y to z w. Find the joint density via the Jacobian. Then integrate out w for the marginal. Define west equals the square root of minus 2 log x times sine of 2 pi y. The pair z, w shares a common radius r equals the square root of minus 2 log x and a common angle 2 pi y, forming a polar-like structure. The key identity, z²+w² equals minus 2 log x, because cosine squared plus sine squared equals 1. The pair z, w completely encodes the pair x, y. Inverting for x, from z²+w² equals minus 2 log x. Taking exponentials gives x equals e to the power minus z²+w², all over 2. Inverting for y, since w over z equals tangent of 2 pi y, we get y equals 1 over 2 pi times arctangent of w over z. The domain of z and w is the entire real plane. The Jacobian of the inverse transformation is the 2 by 2 matrix of partial derivatives of x and y with respect to z and w. The four partial derivatives are partial of x with respect to z equals minus zx, partial of x with respect to w equals minus wx, partial of y with respect to z equals negative w over 2 pi r squared, partial of y with respect to w equals z over 2 pi r squared, where r squared equals z²+w². The determinant equals minus zx times z over 2 pi r squared, minus the quantity minus wx times minus w over 2 pi r squared. Combining gives minus x over 2 pi. Substituting x, the absolute Jacobian is e to the minus r squared over 2, divided by 2 pi. By the change of variables formula, the joint density of z and w equals the joint density of x and y, evaluated at the inverse, times the absolute Jacobian. Since x and y are independent uniform 0 to 1, their joint density is 1. So the joint density of z and w is 1 over 2 pi times e to the minus z²+w² over 2. This factors into two standard normal densities. Z and w are independent, each following a standard normal distribution. To find the marginal density of z, integrate the joint density over all w. The standard normal density in w integrates to 1 over the entire real line. So the marginal is 1 over root 2 pi times e to the minus z² over 2. Z follows a standard normal distribution. This is the Box-Muller transform. Starting from two independent uniform 0 to 1 variables, the transformation produces a standard normal random variable.